Hi, everyone, and welcome. Thank you so much for joining us today. My name is Katie Klotz, and I am the Community Manager here at RoboNation. We're excited to have you with us for an introduction to distributed multi-agent robotics and navigation, presented in partnership with our friends at Integer Technologies. At RoboNation, we're all about connecting students, educators, and professionals through hands-on robotics experiences. Today's session is designed as an accessible introduction to how teams of robots communicate, navigate, and work together in the real world. We're thrilled to welcome our speaker, Ishan Agrawal, an autonomous systems engineer at Integer Technologies. Ishan works on control and autonomy software for underwater defense systems and will be sharing how these technologies are developed and applied. Feel free to drop your questions in the chat during the talk. And with that, I'll turn it over to Ishan.
Thanks, Katie. Hi, guys. I'm Ishan. I'm the Autonomous Systems and Sensors Engineer, as you just heard. I'm based out of Gulfport, Mississippi. And just a little background about what Integer is. Integer was founded in 2021. It's a defense tech software company that bridges research and puts it into action. We work in multiple different domains, ranging from unmanned systems to cyber-physical resilience. A lot of advanced manufacturing, power and energy system, and sensors and perception. A lot of my work at Integer deals within the first two buckets over here, unmanned systems and sensors and perception. Sort of who we work with, like Katie mentioned, we are a defense contractor, so we have a lot of defense government partnerships. We also have a lot of industry partners, like Hui, Metron, Chance. These are the ones that sort of are the hardware component. And the university partnerships are where the main research is occurring, and we translate it and make it into a product for the industry partners. Some of the university partnerships include University of South Carolina, where the headquarters is, University of Southern Mississippi, where I'm based out of, and a lot of other schools. LSU is another prominent one in Baton Rouge. So the agenda for today's webinar is going to be a brief introduction to what multi-agent systems or multi-agent robotics are, some motivation taken from nature. I'm going to talk about the mission constraints and some provable guarantees for such systems. Then we'll talk about how do we model a multi-agent system, and then go into navigation and obstacle avoidance techniques. And I'll end the webinar with some simulation videos of my current research. So as evolution has sort of shown us, there is strength in numbers. Over here, we can see a formation of bird flight geese specifically, and they like to flock together to not only increase their navigation capabilities, but it also helps them sort of optimize the aerodynamic forces when they're flying in a formation. It also leads to higher survival chances, as they can sort of threaten predators as a big whole unit. And they can sort of help each other out. It's easier to not get lost when you know where your neighbors are. Sort of applying that concept to the modern world of robotics. Over here, we have sort of like this simulation demo of a bunch of drones that are trying to traverse this environment with some obstacles in between. What capabilities multiple agents or multiple drones in this case gives us is that we can rapidly cover a larger area, whether we're trying to do like a search and rescue mission or just general mapping and understanding what the environment we are in. And because there are multiple of these agents, there are fewer failure points to guarantee mission success. So when we think about birds, when we think about animals sort of behaving, coordinating together, they don't have a central controller. So who is controlling a multi-agent system? Over here, we can see the three different sort of groups of controlling methods. The first one being like a centralized control architecture, where you have one node that is gathering all the information about every other node's state and is telling what everyone else should be doing. The second is like a decentralized approach, where you have a few nodes that are talking to each other, but those nodes have then the neighbors that only listen to them and don't have an overall connectivity to the remaining graph. And on the right-hand side, we have distributed systems, where sort of You can prescribe how the agents can talk to each other. There really isn't any hierarchy. And the decision-making is sort of spread across the group. There's no single unit that's calling all the shots. So with this in mind, what are some constraints that multi-agent systems sort of have? On the right, we can see like this picture of ants that form a bridge to traverse a gap. And I really like this example because there isn't a single ant that knows what the length of this gap is, but they sort of all work together, they pass the information around and have sort of an emergent behavior come up that lets the entire colony progress and lead to better survival benefits. And in the same way, as we spoke about earlier, a flock of birds find it easier to traverse and can go longer duration in their flight when traveling in a group. So some constraints when we think about these systems, we don't want these birds to be flying into each other. That wouldn't be good. That would just hurt the system. We also want the birds to go from point A to point B how they had planned and sort of have some convergence guarantees about this. And while doing this, we don't want any bird to be left behind or any ant to be left behind. We want the whole group to do this traversal together. We don't want anyone to be left behind. So let's sort of define these constraints a little more. Collision avoidance can now be thought of as these small nodes, think of them as birds, that have a certain radius of safety to them. And we don't want that radius of safety to overlap, or else that would be flying on top of each other or hurting the other bird. So we can say when the norm between an agent state xi and its neighbors xj at any point in time is greater than the R safe for all I that's not j, so for every node that's not myself, and for all of time, that can sort of guarantee that throughout the mission, we won't be having any collision avoidance. Goal convergence, in a similar way, can be defined as seeing the limit as time goes to infinity. The difference between your goal state and your own state should go to zero. That basically means if I had planned to go to the corner of this room, but as time progresses forward, I should get closer to the goal. And eventually, I reach the goal. These guarantees come from sort of a controlled theoretic approach and will be discussed later on in the talk. And the last sort of guarantee that we'll be talking about is how do we make sure the connectivity is maintained? And this is like the main core of this webinar is these agents that were prescribed to be edges that can communicate information with each other. How do we ensure that as they all move in this workspace while avoiding obstacles or doing whatever mission they're supposed to do, they are not breaking this communication radius or they're not losing connectivity with other agents. So the way they formally describe this is that the norm or the position between two agents is always less than the communication radius R for all agents that are in the initial set. So E0 just describes the initial set. Again, we'll be talking more about what these notations mean. So sort of an overview of what we just discussed. We sort of have the safety of the system, which basically says we have a set of states in our workspace that are bad, that sort of result in collisions or result in sort of harm or agents getting hurt. And we don't want to reach those states. And mathematically, we can ensure whatever control algorithm you're building never enters the states. So using those two conditions for safety and the condition for reaching the goal, we can sort of now think about how would a multi-agent system do a mission with certain guarantees and prove that it can hold for any configuration of any environment. So hopefully everything is making sense so far. Here's a small sort of question. Do we think both of these can be achieved at the same time? Could we have connectivity and no collision always be satisfied? And I'll just wait for a few seconds in case there are any comments or answers in the chat.
While you're waiting, Ishan, there have been a couple of questions in the chat that have come through. Do you want to take a second and answer this? Perfect. Okay. Our first question is there anything going on in Colorado this summer?
I guess time is going to pass in Colorado. I'm not sure what's happening in Colorado specifically.
Maybe summer plans. Maybe somebody wanted some summer plans. But here's another one. Are robots using some kind of edge AI, or is it just a distributed controller?
So I will not use the words AI in the entirety of this talk. This is pure math. There's no sort of AI LLMs being put on these devices right now for the purposes of this webinar. So this could be marketed as edge AI for the right marketing team, but I would not say this is edge AI.
Perfect. Beautiful. Thank you very much.
Okay. Have there been any sort of comments about this question, whether these two things can be achieved, or we can move forward?
Let's see, as long as the safe radius is less than the connectivity radius, it is possible?
Yeah, that's exactly right. So you have to make sure to play with these two constants, which make sure that the system is safe, but also not too far away that the agents are being pulled. So what I want to highlight with that exact point is that there's sort of this tension between achieving these two goals. You can't always have a fully connected graph where every agent is trying to do everything together and also not having collisions, because the controller needs to account for that tension. Okay, I'll continue with the webinar. So how do we formulate this navigation problem now, like we just spoke? Given that we have a workspace, Omega, and we have obstacles, let's just call them OFI, and there's a target position, X star, that's in the interior of Omega, the navigation problem is to find a controller, a continuous controller U that maps from the workspace to RD, which is the domain of control, depending on the system. So like we just spoke about, the three constraints that we have is to keep the robot safe while avoiding obstacles. So that's point one. The second one is convergence. We want these agents to go to the target. We want them to do the task they were assigned to do. And the third is connectivity, is these agents in the way the graph is prescribed. As time goes forward, the graph stays connected. Awesome. So with this in mind, how do we start modeling multi-agent systems? This is going to be a little bit of a background in graph theory. So please hold your wheels. It's going to be like 5 minutes, but sort of sets the basis for what's to come ahead. So the first definition we have is an undirected graph, where we have a graph G, which is defined by its vertices and edges, V and E, where each vertex basically represents a robot and the state space it can take in. The second component, edges, are prescribed by the user or by the mission that indicate which vertices can talk to each other. So an edge I, j that belongs in E indicates that agent I and j can communicate. We can then define the neighbor set, which is the set of all such vertices where the edges can talk to each other. So these would be the neighbor set. So 1 has neighbors with 2 and 3, 3 has neighbors of 5 and 4, and 3 also has neighbors of 1. So the neighbor set for 3 would be 1, 5, 4. Okay. The dashed blue circle over here shows the communication radius, so they have to be always within each other. With graphs and vertices and edges in mind, we can define the adjacency matrix, which is populated to be 1 if there is an edge for that I, j pair, and it's 0 if there isn't an edge for that I, j pair. So in one of the future examples, we'll see that agent 1 and 2 have an edge with each other. So there is 1 and 1 populated, but 1 and 3 do not. So there's a 0 over there. And the same way, the degree matrix can be defined to be the number of connected components for each robot. So the degree matrix for number 2 would be the sum of the the components it has edges with. So 1 plus 1 results in 2. So with adjacency and degree matrices, we can compute the graph Laplacian, which is a really important matrix that is a subtraction of the adjacency from the degree matrix. So with these two earlier matrices, you can compute the Laplacian matrix that looks something like this. By the looks of it, it doesn't really look interesting, but it does have certain properties that are really interesting. So here's another question out for the audience. What could the eigenvalues of this matrix represent? And I'll wait again if there are any comments.
If anyone has any ideas, now's the time. You may have stumped them.
That's fair. So I'll just go ahead. It is not very well known, but the second smallest eigenvalue of this matrix is called the algebraic connectivity, or the Fiedler value of G. And it measures how well connected the graph is. So the second smallest eigenvalue tells us about how fast can this network or this graph perform consensus, something I will define as we get on. But the takeaway from this is, as you subtract out these two matrices, you get this Laplacian matrix that can then be used to tell you about how this graph is going to behave as it moves forward in time. Okay, so what is consensus? The simplest distributed protocol, and distributed because we want each agent to be able to make decisions by themselves. There's no AI, there's no one telling them what should be done. So how does an agent himself or a robot himself make a decision as to where I should move forward in time? So we'll assume the continuous time dynamics for this agent are simple single integrator holonomic. So x dot is equal to u, which basically means if I give you a control input, you can perform it without doing any maneuvers. For example, a car is non-holonomic because a car cannot go sideways. You have to sort of go forward and then take a turn to go sideways. Whereas a crab, for example, a crab can point itself in any direction without having to reorient because of the way its legs move. So a crab sort of follows x dot is equal to u dynamics. And what xi of 0 is equal to says is the initial state of the system is defined to be xi naught. So the control input for a really simple distributed protocol can be shown as a summation of its own position subtracted from its neighbor's position. So xi being my position, subtracting it out from where my neighbor is, and I want to use the sum of all of those subtractions across my neighbors to tell me how I should move if I want to do consensus. Sort of a good graphic I like is these sort of little robots that all have their own perception and they have their own observations of the environment. And they can use these local observations to perform cooperative behaviors. And consensus sort of forms the backbone for this. So, sort of re-expanding that, we can see that you can break out the neighbors because we know how the neighbors are connected within the edges, and then you can reformat this equation to include the Laplacian. So we have x dot is equal to minus Lx, and you can solve this using any ODE solver. So here's a small simulation where you have two nodes that are trying to do consensus, which is to say they are going to meet at a point that they both have agreed is the center for the two neighbors in this case. And we can see as time goes forward, each neighbor is computing, oh, I should probably move over here. I should move over here. And eventually they reach the central state, which I don't think, the video doesn't go that far. But yeah, as time goes to infinity, they end up moving together. So sort of another poll or a question for the audience. Which one of these network structures will reach consensus the quickest? Or if you want, you can rank these. And I'll wait again for any audience if they have any answers.
I think people are still thinking. I'm going to guess
Yeah.
the connected star.
Mm-hmm. And what's like the intuition behind that?
It looks like the points had sort of a way to meet, like you said. There was a line for them to meet.
Mm-hmm. They can talk to each other because there's a line that's connecting the 2 points. Yep.
Oh, wow. Even though I gave it away, does anyone have any more to say? Oh, looks like the consensus was connected. We have a very smart audience.
Awesome. So that is right. And like you just spoke, we can calculate the second smallest eigenvalue for these. And we can see a small simulation of each one of these sort of trying to come together. And the path is definitely slower than the cycle, but they all eventually come to the center because they're all trying to move towards where its neighbor is. And for the connected, it just contracts eventually because everyone knows. Everyone is talking to every other neighbor, and it's a fully connected graph. You can see the lambda 2 values, 0.7, it's getting close to 1 because it had a cycle. 0.2 is not that good, whereas 7 is really, really good. And it was 7 because of the number of agents. So now that we know what graphs are, what consensus is, how do we get these agents that are moving by themselves to avoid obstacles and navigate to a target? To do that, we'll first sort of ask another question to the audience. Which one of these approaches produces a time-dependent path? And Katie, you're more than welcome to take a guess again.
I think the dots were about the height of my expertise, Ishan, but let's see. We'll give people a minute to see what they think. Everyone's been right so far, so maybe keep it
Have a good
going.
audience.
All right, I'm going to take a guess. I'm going to guess motion planning, the one on my left.
And what's sort of like the intuition behind? You are right.
It kind of looks like there's connection established. It's not a technical response, but oh, someone said the APF.
Oh, okay.
You might have to do some, no, the left one. They said you might have to do a little, we'll do a little explaining, Ishan.
Okay. Yeah. So it is sort of a little counterintuitive when you think about time dependency with trajectories, but the answer is motion planning using Dijkstra in this example. So why it is a time-dependent path is because it's tracking a pre-computed trajectory. And Dijkstra is a really good algorithm, or A star, RT star. These sampling-based methods give you a path. They don't give you how you should follow this path. But once you have this path, once you have these series of points that you need to go to your destination, how do you track that? How do you follow that trajectory? You end up writing a controller that is dependent on these series of points as a function of time. So your control input becomes a function of time. So it is dependent on both where you are and what time of the trajectory you are. So this results in a non-autonomous differential equation when you close the loop. On the other hand, with reactive navigation that use artificial potential functions, you have a real-time control law that's produced solely from the current state. It combines both plat panning and control, which results in an autonomous differential equation. And because it's not dependent on a trajectory, it only has to compute the gradient of wherever it is. And that removes the dependency of time. So it just needs to know where am I on this map and what's the gradient. And that will take me to the target. So with this in mind, we can now sort of define the workspace that we're going to be moving in. We're going to define the workspace omega to be a subset of RD, which has piecewise smooth boundaries denoted as omega or del omega, which is this box, as you can see. Obstacles can be defined as the connected components of RD minus omega, so all the holes within this workspace. And because there are finitely many obstacles, we have finitely many components of the boundary of omega. And all of this is useful for when we end up doing some of our proofs. A robot that has a certain radius, as it's traversing this environment or workspace, it needs to account for its own dimension. To solve it easier for our ODEs, we can buff up or expand the obstacles by the radius of the robot. In this way, we can treat our robot as a point source. So we have a point robot that's in this workspace omega r. And all it has to do is navigate these obstacles that have been buffed up by its own radius. Once we have a way to use a point source, and we know it's a single linear system with simple dynamics, we can define navigation fields. This was a lot of the work that was done by my advisor, Dan Goralnik, and Fred Zegers, which looks at computing this map N, which maps from omega cross omega to RT, which satisfies the following three conditions. The inner product of the navigation field with the gradient of the boundary of the obstacle is always greater than 0, which says it will always move the robot inside the workspace and away from obstacles. The fact that it is inside the workspace is really important because you don't want the robot to go to the boundary and have it been pushed outside of the boundary because there's an obstacle over there. So there's sort of an interplay between how much the obstacle is pushing the robot away and how much the boundary is also pushing the robot away. The second condition is z is equal to y, which basically says the target for this navigation function is the only stable equilibrium for this function, which means there are no ways for it to get stuck in a local minimum because there is only a unique stable equilibrium for this system. The third condition for a navigation field to be functional is all of the solutions of x of t should converge to the target, which is y, as time goes to infinity, for almost all initial conditions within omega. The convergence to our targets is almost in all cases because there's a set of measure zero exceptions, which is never really shown in real world because as we have sensor noise and localization noises, you always end up in the set where you're not in measure zero. So you will be pointed to the target. Okay, so now we know how to avoid obstacles and how do we get to the target, but how do we get the graph to do this together and not be stuck or not have an edge that's cut off? So we can define what graph maintenance is using the earlier defined terms, and we can see a configuration, a valid configuration, which is the capital X, is defined as all the positions for our robots that ensure the graph is connected within the bigger space. So all we are concerned about is this are valid. So the communication radius valid configurations of a graph are the ones that we want to maintain as time goes on. And this sort of the construction of the controller ensures that every solution for a differential equation that starts within a valid configuration remains valid for all of time. But how do you do this with dynamics or with multiple agents that are so spread out? We can use springs. Springs are engineers' best friends. They provide a lot of good ways to simplify systems. And over here, we can imagine the edge that is connecting which agent can talk to which other agent. We can imagine it as a virtual spring. And this virtual spring can have a spring constant, or no longer a constant in this case, but an edge tension R, which is dependent on how far away or where it lives within breaking off. And these parameters can be tweaked to make sure as our system is moving across time, the agents are right on top of each other or a little far apart, but are not being left behind. A lot of the math, I think, is beyond the scope of this presentation, so I've skipped a good chunk of it. But if there are any questions about how the derivations are done or how the convergence guarantees are shown, I'll be happy to get into it. And it's also available in my thesis. Okay, so now that we know what graphs are trying to be maintained, how do we design the controller? Because each agent should be controlling themselves. They are not being told what to do. They can talk to the neighbors they're prescribed to talk to. So we designed the controller to be very similar to the consensus structure, where you're adding fields on top of other fields. But we use the navigational field concept and append it onto the consensus. So it's like a weighted average, but a little more asymmetric because of the rescaling factors and the tensions. For the cases of my thesis, we assigned a leader and we assigned a bunch of followers whose task was to just stay close to the leader and follow whatever the leader is doing. And the theory works in a way where the leader's task can be any bounded signal, which can be generalized to mean a lot of things. So here's a short simulation demo showing the contractive case of the PNP. And you can see as all the agents sort of just get on top of each other and they're all trying to follow the leader as closely as possible. And the leader is navigating around the obstacles and going towards the target. As it gets far enough from the obstacles, it sort of speeds up. And these are the gains that have to be played with to make sure the system is not behaving in erratic ways. Give it a little more time. And yeah, you can see the leader and sort of its followers have all moved towards target with no edges breaking. And this, in some sense, was a lot of cheating because they were literally on top of each other. But here's an example where the lazy case where they're sort of keeping a distance from each other. So as the leader goes, it starts pulling the two neighbors it was attached to. And those two neighbors pull its own neighbors. And eventually, the whole group is sort of moving in this playground, swimming pool workspace. And as the leader reaches the target, because of that constraint, the edge is still strong. The tension is still there. So in this case, the following neighbors do not reach the target, but the leader does. Yeah. So I'll sort of end this talk with some research avenues. This is only one way of solving the problem. Like I said, there were three main constraints that we're trying to find the balance between. This was a very recent paper that came out, which uses spline-based trajectory planning, super potential to be applied in sort of multi-agent senses where you have a map of the environment and you're trying to find the best path for all of your agents to go to. But with all that said, I will like to end my talk. If there are any questions, please feel free to email me. Please ask them in the chat right now. And yeah.
Ishan, thank you so much for this incredible presentation. Thank you to everybody who joined us today. We hope this session gave you a helpful introduction to distributed multi-agent robotics and sparked some new ideas for your own work or studies. If you enjoyed this webinar, be sure to follow RoboNation on YouTube and stay connected with us for future events and resources. We appreciate you taking the time to be here. Ishan, thank you again. This was absolutely incredible. And we hope to see you all again soon. Have a wonderful rest of your day.
Thank you. Yeah, see you guys.